Hello everyone, I'm a PhD student at EPFL in the Laboratory for Quantum and Nano-Optics, and I'm going to be talking about single phonon counting and light vibrational entanglement. So in my talk, let's see if I can get it to work. Okay, so in my talk, I want to talk about how to prepare quantum states of vibration at room temperature. So for this, I will be talking about high-frequency Raman active phonon modes, so in the tens of terahertz, which you can find everywhere in crystals and molecules in nature. And I want to talk about how to prepare them into a well-defined quantum state and how to measure their temporal evolution. And this will be done by combining spontaneous Raman scattering and single photon counting. So I guess everyone here is familiar with single photon counting, but I want to take a second to give a very quick reminder about Raman scattering, just so that we are all on the same page. So in spontaneous Raman scattering, you can have two types of events. So you can have Stokes scattering, where you create a phonon plus a Stokes photon. So you come in with an incident radiation, and you emit a photon. You create a phonon inside your material, and you emit a photon that has the energy of your incident radiation minus the energy it took to create this phonon. And you can also have the opposite process. So you come in with a laser, and you annihilate a phonon inside the material. So now your scattered radiation has the energy of your incident radiation plus the energy absorbed from the phonon. And something very important about this process is that it has to find a phonon for it to be possible. So it depends on the occupancy of the phonon mode you are looking at. And this we'll be using throughout all the rest of the talk. So now talking about, in particular, I'll be showing experiments done on diamond, done on the 40 terahertz phonon mode in diamond, which has an energy of about 165 millielectron volts, which at room temperature gives you an occupancy of about 10 to the minus 3, which is great because at room temperature, we are already essentially in the quantum ground state. So usually for optomechanical experiments, you have to cool very aggressively inside a dilution refrigerator, sometimes with extra laser cooling. But here, just because of the high frequency, we are already essentially in the ground state at room temperature. And I think even though we are essentially in the ground state, the phonon distribution is given by a thermal distribution, which means that if you're able to isolate a single spatial and temporal mode, you can observe bunching. So if you just look at the anti-Stokes signal from a laser, and you do a Hanbury-Brown twist interferometer, and look at the correlations between them, you can find that the signal is bunched. In the ideal case, you would expect a G2 of 2. In practice, we have other sources of noise, so we measure something that's slightly smaller, but we can measure thermal statistics from this phonon mode. So for this, you have to isolate a spatial and temporal mode. So for a temporal mode, we have to go to ultra-fast optics. So the downside of working with phonon modes at room temperature is that they decay very quickly. So we use 100 femtosecond pulses from a TISAF oscillator in order to isolate a single temporal mode. And a funny result of this is that even though the thermal occupancy is at around 10 to the minus 3, you're still more likely to detect multiple phonons at the same time during your experiments. Now, we have thermal statistics from the phonon mode, which is what we expected. But the question is, how do we go from this thermal state to a non-classical state? And here is where the Stokes interaction comes in. So if you have a Stokes interaction, Stokes scattering, you create a squeezed state. So you can have either 0 Stokes photons and 0 phonons. You can have 1 Stokes photon and 1 phonon. You can have 2 Stokes photons, 2 phonons, and so forth. And this is actually very similar to parametric time conversion for those who are familiar with it. So we have Stokes scattering from 1 laser pulse, and then we have single photon counting. So when you have single photon counting, we detect a photon, we can be sure that we are not in the vacuum state. And we only have these higher order terms. These terms depend on the probability of scattering a photon. So if you work in the low probability regime, you can have essentially just the first 1 Stokes, 1 phonon event. And this gives you your n=1 Fock state if you are working in the Fock basis in quantum optics. And after that, in order to measure it, you can have again anti-Stokes Raman scattering from a second laser pulse. So we want to have we want to measure the temporal dynamics. So it's important to use a second laser pulse for this. And what we do in order to distinguish, for example, an anti-Stokes or a Stokes photon from the first and second laser pulse is to use 2 different colors for lasers. One laser is a TISAF oscillator, and the other comes from an optical parametric oscillator that is synchronized with a TISAF. And in this experiment, we can have first the Stokes photon that tells us that we prepared the state in the n=1 Fock state, which is what we wanted, and then the anti-Stokes from a second laser pulse, and we can do a Hanbury-Brown twist measurement and look at the autocorrelation of the anti-Stokes photons now. So here we're looking at the conditional statistics of the anti-Stokes photons now. So if we only care about the anti-Stokes events when we observe the Stokes scattering before, and if we do that, we see that when the preparation pulse arrives after the readout pulse, we see our same thermal statistics, nothing has happened. But once we have a preparation pulse and then we read out the state, we see that the statistics go from having bunching, or thermal statistics, to having very sub-Poissonian statistics. Which means that here, the vast majority of cases, when we have the second pulse finds 1 and only 1 phonon to annihilate, which means that we are indeed preparing on our n=1 Fock state. Now, we know that we can prepare the n=1 Fock state, but we want to know more about how the state evolves. And for that, we can look at the correlations between just the preparation pulse, the Stokes from the first laser, and the readout pulse, so just the anti-Stokes of the second laser. So we can stop doing this Hanbury-Brown twist interferometer and just look at the correlations between one scattering event and the other. And here, if the events are mediated by the same phonon, we expect them to be very highly correlated. So as I said before, the anti-Stokes scattering depends on the occupancy of your phonon mode. So when you don't prepare your state previously, you have 10 to the -3, but just after preparing your state, you have 1. So you will expect a very strong correlation between them. And this is exactly what we see. When the lasers overlap in time, we see a very strong correlation between the Stokes between creating a phonon in one pulse and annihilating a phonon in the other pulse. And as we increase the separation between the laser pulses, this correlation decreases. And if we wait long enough, this correlation completely vanishes. So we can look at the second order cross correlation between the Stokes of one laser and the anti-Stokes of the second one. And with this, we can map the lifetime of the phonon mode we are observing. So we are creating a phonon at 0 time, but this phonon has some time, can decay over time. And if we wait long enough, it will get to the point where we can no longer find that phonon we are preparing. And with this, we can measure the lifetime of the phonon mode. As I mentioned before, this lifetime is quite short. So here is below 4 picoseconds for diamond. And the dynamics are the same for this second order cross correlation and the conditional autocorrelation of the anti-Stokes. So with this, we have a well-defined quantum state, but we also want to go a bit further and extend our scheme to prepare entangled states. So because of the time, I'll just sketch briefly how we do it. So in order to prepare an entangled state, photon-phonon entangled state, we take 2 temporal modes, and we want to prepare them into a superposition. So having 2 temporal modes is fairly straightforward. You can send your set of laser pulses through an unbalanced interferometer, and this will give you an identical set of laser pulses. And we can have these two interacting with a sample. And you have a chance of having this Stokes, phonon, anti-Stokes event either at one time given by your first set of laser pulses, or a second time given by your second set of laser pulses. And what we do is that we additionally add polarization information into each of these modes. So the pair of events that can happen at the early time will give you vertically polarized photons, and the pair that happens at a later time gives you a pair of horizontally polarized photons.
Nicht geklappt, hat jetzt nicht geklappt. Remo bin ich jetzt drin.
2 minutes.
2 minutes, great. So once we have these two possible sets of, once we have these two pulses that can give either 2 horizontally polarized photons or 2 vertically polarized photons, we can overlap them in time again and end up with only polarization information. And by erasing this information, we can end up with a superposition of horizontal or vertically polarized pairs of photons. After that, we can use this for a CHSH inequality measurement. So hopefully everyone is somewhat familiar with Bell's theorem and Bell inequalities. The CHSH inequality is one specific form of that, and it requires measuring pairs of entangled photons or entangled particles in different measurement bases. So we control the polarization to rotate our measurement bases and perform a standard CHSH measurement. And doing this, we observe a violation of this CHSH inequality. So this means that if you go above 2 for this CHSH parameter, you have a result that cannot be reproduced by any theory with local hidden variables. So this is the most stringent test of entanglement that we currently have. So to summarize, we can use Stokes and we can use Raman scattering and single photon counting combined to prepare a phonon mode at room temperature into the n=1 phonon Fock state. We can use this to measure the lifetime of this quantum state, and we can even extend this scheme to prepare entangled photon-phonon states that have correlations that are strong enough to violate Bell inequalities. So with that, I'd like to thank everyone for your attention. And I'm open for questions.
Yeah, thank you very much, Santiago. Quite impressive results preparing the phonon-Fox state and equal one at room temperature and entangle them with entangle them. So it's really great. So our questions.